Hello and welcome to our second lesson on polynomials. And what we've learned so far is how to work with complex and radical numbers. It's a review from earlier. Today we're going to, and actually the rest of the chapter, learn about a family of functions called polynomials. You've seen them as linear, quadratic, maybe even cubic. And then later in the chapter we'll do something with rationals, which means similar functions but negative exponents. So, to get going here, today what we want to learn is how to identify the degree and leading coefficient of a polynomial, how the degree and leading coefficient will affect the graph, and how to describe some key features of a polynomial. Finding zeros and factoring. Where does the function equal 0? What we want to do here is focus on what makes the function equal 0, and if the function is factored, we can see values for x that will make the whole function equal 0 because we can get one of the factors to equal 0. So a rather simple quadratic here, we would see that x squared minus x minus 2 factors into x plus 1 times x minus 2. Knowing that you have two values that are multiplied that make it equal 0, at least one of them must be 0. That means x plus 1 or x minus 2. So we just choose the opposite value. Negative 1 plus 1 is 0, or 2 minus 2 is 0. And those are both zeros of the original function, where the original function, it may not be as obvious. Some basic polynomial examples. Quadratic, you've seen, has a degree 2. Cubic, a degree 3. Quartic and quintic, not used a lot in this class, but 4 and 5 is the highest degree for those polynomials. And well, we could keep going. And some basic definitions. The degree of a polynomial is the same as the greatest exponent of the variable. And we typically use x for this. The leading coefficient is the coefficient of the highest degree polynomial. And the zero of a function f is an x value. We use the letter c where f of c equals 0. So the value we would call a 0 is the x value that when plugged into the function makes the whole thing equal 0. And essentially that's an x-intercept. What degree is the function? And what is the leading coefficient of the function? So if we look at f of x, we look for the biggest exponent, in this case 6. We would say the degree for f of x equals 6. And then the number in front of that term will be what's called the leading coefficient. And I will often just use LC. All right. Look at g of x. It's a little bit deceptive. You need to look for a polynomial in standard form, and in this case we'd have to rewrite it, or since the question is simply to find out some values, we could just look at it, but I'll write it in standard form, helping us see that 7 is the degree, and then the leading coefficient is negative 4. Okay, and those two things are what really affect the shape of the graph, so we'll want to be very clear on where we find those values. We get to something called the fundamental theorem of algebra. What it states is that an nth degree polynomial function has exactly n zeros, and this means there are n zeros, n values of x you can plug into the function that make the graph cross the x-axis, or the whole function equals 0. So if you have a linear equation at degree 1, you would see that the line crosses the x-axis in exactly one place, and actually that would be a real 0. If you have a parabola, you'll have exactly 2 zeros. We talk about real and complex. A while back you were taught that there are the quadratic formula, and we always made sure the radical term, the discriminant it's called, was a positive value, But if you had a parabola that opens up and is above the x-axis, you're still going to have two zeros. They're just going to have i's in their solution, imaginary solutions or complex. So let's take a quick look at the graphs of quadratic functions. There's a few features we want to point out. The y-intercept is an obvious one, so we look at that, but it's not the most important necessarily. We obviously care about the vertex, something we'll call a turning point, and as well what the zeros are from the fundamental theorem of algebra. So if we look at some of these examples, you'll understand how they compare in relation to their zeros and vertex and how they open up or down. And we want to get familiar with those things and how that's indicated by certain values, specifically the leading coefficient and the degree. You'll notice a negative 1x squared opens down, a positive 1x squared opens up. Same thing down here. The negative 1x squared opens down, positive 1x squared opens up. In addition, the y-intercept is obvious when we have a graph in standard form. We just plug in 0 for x and the variable terms go away, so we're just left with y-intercept that I've written in blue here. There's also always two zeros, but in this case on the top we're going to have two real. This one we're going to have one real, something we're going to call a double zero. And then these are both going to have complex zeros because it doesn't cross the x-axis. And so we got some stuff to get into here. Consider the zeros for the following quadratics. In this example, we're going to have two zeros that are real on the left. We could say x equals negative 2 and 3 are zeros. For the second example, the zeros, and this, we're going to call it zeros, but it's x equals 1, 2, 3, 4, but it's a double zero. So we would say 0 of multiplicity 2. It's a multiple zero. And then the last one, they're going to be complex zeros. We can't tell what they are from the graph. Takes a little more algebra work, but those will be complex zeros. So get familiar with the amount as well as the type of, whether it's a multiple zero or a complex zero. Back to the point about the vertex, as a graph turns and goes from increasing to decreasing or the other way around, decreasing to increasing, in red here we point to all the actual turning points, places where things go significantly different in the graph. And then there's something called an inflection point, a little tougher to see or notice, but it's where the concavity changes. And what you want to notice there is if you are increasing but increasing at a different rate and then changing to still increasing but at a different rate, there's a place, it's not always obvious, that the graph has gone from increasing, in this case, at a faster rate to then increasing at a slower rate. And that's, you typically look at something like this and call it like an exponential kind of a thing where it's increasing faster and faster, but when it gets to the inflection point, that's when it changes to increasing at a slower rate. So there's something to pay attention to, and it's rather subtle. I think you'll notice though. And now we want to ask some questions. These are going to be fundamental questions we get into for all polynomials. So as they look easy for quadratics, be thinking how you would generalize or expand your understanding to higher degree polynomials other than the ones you've seen for years now in Algebra 1 and Algebra 2. What's the number of zeros for a quadratic? Well, a quadratic is a degree 2, and by the fundamental theorem of algebra, the number of zeros equals the degree of the polynomial. In the case of a quadratic, that's 2. So remember, that will include the complex zeros as well, whether it crosses the x-axis or not. There's a way to make it 0. What's the maximum number of critical points, or changes in concavity, for a quadratic? And remember, that's where the graph may turn completely from increasing to decreasing, or even how it changes from faster to a slower rate. Those are inflection points. There will always be one for a quadratic, and generally there are a maximum of n minus 1, n being the degree, turning points for a polynomial. And last, how many zeros are possible for a quadratic? Well, there are 0 if the quadratic does not cross the x-axis, but there's still zeros. There's just no real numbers. They're going to both be complex. 1 if it just touches, that would be a 0 of multiplicity 2, or we could call it a double 0. And then last, if the quadratic crosses the x-axis twice, there are 2 real zeros. That was basically what you dealt with mostly in Algebra 1. Didn't have to deal with complex numbers. Okay, this is the graph of y equals x minus 4 squared. So it's just translated to the right 4. And what I want to ask is, what's unique about this 0? We've talked about it. It's not just a 0, it's a 0 of multiplicity 2, or something we could call a double 0. Now you'd be thinking, if this polynomial had a higher degree, we obviously could have higher degree zeros as well. And now we look at graphs of cubic functions. Similar view we want to take. What are the critical features happening here? The y-intercept's easy to find, so I pointed those out. It's not a really critical thing. It's just useful for sketching the graph with limited information. But the zeros we definitely care about, as from the fundamental theorem of algebra. So if you look at this top left one, we've got zeros of multiplicity 1 all the way across the board. They're all real zeros. On the right, we see there is a 0, but there's only 1, and it's a degree 3 polynomial. It stretches. You might remember this from a direct inverse, y equals x cubed. So what we'd call this one is a degree with a 0, with a multiplicity of 3. And now we look at the equation in the bottom left, and what you notice here is there's a few negatives, so it's a little deceptive, that negative, and of course that minus 2. The graph will look as shown here. The graph will look and now we look at this graph in the bottom left, and there's a few negatives in here. It can be a little bit deceptive. You might think this thing would translate to the right, but because of the negative out in front, the graph is shown above here. There's a 0. It's a real 0, but it's a 0 of multiplicity 3 in this case, just like the previous problem. And now we look at this last example, and we notice that it has 3 zeros that are real, just like the first example, and they each have a multiplicity of 1. You may have noticed also that the leading coefficient has an effect. If the leading coefficient here is negative, it really ends up looking kind of like a negative slope. And if the leading coefficient is positive, it has a positive slope with some squiggles. What is the number of zeros for a cubic? Well, as we discussed earlier, the fundamental theorem of algebra tells us it's a degree 3, so there'll be 3. Some may be real, some may be complex. How many critical points for a cubic? Generally, there are a maximum of n minus 1 turning points for a polynomial of degree n. So for a cubic, that means you'd see 2 actual turning points. There may be inflection points, just like we saw. This is an inflection point. It's still a critical point. It's not an actual turning point. So you want to get the terms critical, turning, and inflection points. Those are all different. So these are inflection points here, or an inflection point. These are actual turning points because the graph changes complete direction from increasing or decreasing to the opposite. And then last, what's the maximum number of real zeros? If there are 2 or 3 real zeros, they'll cross the x-axis twice, or one is a double 0 or triple 0, and there's no complex. If there are 1, then it crosses the x-axis once. The other two are going to be what's called complex zeros. Okay, graphs of quartic, these are degree 4, and you can start to see some patterns here. Notice the number of zeros. You're going to have 4. You're going to have 2 real zeros, and each of them are double zeros. Also notice that leading coefficient is negative, and this thing opens down, much like a parabola would if it had a negative in front of the x squared term. If we look at this second one to the right, there's 1, 2, 3, 4 real zeros. They're all different. We would expect that, and the leading coefficient was positive. Now, when you get to degree 4, you can really see some unique things. You might notice that there are some, like this is an inflection point. It's kind of strange looking. You can also look here and notice that there's going to be a complex zero because you can't get x squared to be negative. X squared will always be greater than or equal to 0. So with x squared being positive or 0 and 3 being positive, you need x to be some kind of an I where when you square it you get a negative 1. So that'll be something we look at as well. All right, well this is going to be one of your generic looking polynomials, the graph. And what's the lowest possible degree of the following function? Well, if we said that the degree minus 1 tells the turning points, we could say, if we just make some assumptions, 1, 2, 3, 4, it looks like 4 clear turns. Since there are 4 turning points, we're going to have 4 plus 1, or 5 for our degree. And based on this answer, how many zeros does it have? If we assume a degree of 5, by the fundamental theorem of algebra, we would see that there are 5 zeros. Some are real, some may be complex. In this case, 3 real zeros would exist. That's where it crosses the x-axis. And you might say, but I only see one spot and then a second spot, but this would be a double zero. We would see it show up as a quantity squared in our factored form. Where are the critical zeros or extreme points? Since there are 4 turning points, there are 4. And where are the critical or extreme points? Well, if we assume a degree 5, then all the critical points are the turning points. They're actually turning points, not inflection. So they would be, if I use this red marker here, they would be labeled the 1, the 2, the 3, and the 4. Those are our critical points. They're turning points. Is the degree odd or even? Leading coefficient positive or negative? Well, since the curve is end behavior that shows, and this is a notation thing, just think of x approaching negative infinity as the left-hand side and x approaching positive infinity, you can think of that as way over on the right-hand side. So on the left-hand side, our function was down at negative infinity, and on the right side it was up at positive infinity. So it looked something like this, where it went down to negative infinity on the left and up to positive infinity on the right. So this end behavior is something we're going to have to get into in the notation for it. The x is the horizontal position. It's going to be the left when it's at negative infinity, the right when it's at positive. And then the f of x is the y position. Is it going all the way up or all the way down? We can think of this similar to a line with a positive slope. Therefore, the leading coefficient must be a positive. We don't know what it is, but we know it must have those characteristics. For a curve with an even degree, we can think of it as a parabola with squiggles in the middle. We have an odd degree, but if it was an even degree, we would notice that on the left-hand side, it approaches negative infinity, but also on the right-hand side, it approaches negative infinity, so it opens down. So the curve opens down and the leading coefficient must be negative if we had an even degree with a graph shown over here. Real quickly, what's unique about this point? You notice that it is what we call a double zero, or a zero of multiplicity 2. Now let's get into this, and we're almost done with the lesson. We're going to start making some potential drawings, or drawings that could be shown to have these features. Okay, let's try to make some sketches here. Draw a cubic function with a negative leading coefficient that has zeros at 1, 2, and 3. Well, 1, 2, 3, I put dots there. To be a degree 3 or a cubic, it could start down at negative infinity, come up, cross over, and look something like that. Or if the leading coefficient was negative, it could have essentially a negative sloped line that has squiggles. That would look something like this. Okay? There's an infinite amount of possible correct answers, but considering that there are two options for how this thing starts and ends, we could look at either of these. But it has to cross the x-axis at those points 1, 2, and 3. All right, draw a cubic function with a negative leading coefficient that has zeros as stated. Go ahead and try this on your own and then hit play. All right. All right, so our possible answers, there's an infinite amount of them, but we would just put a dot at negative 3 on the x-axis, negative 1 on the x-axis, and up at 4. Having a negative leading coefficient makes it look like a relative negative sloped line with some squiggles, something like this. All right. Try this one. Draw a function, a cubic function with a negative leading coefficient that has zeros at negative 1, 1, and 5. Go ahead and hit pause. Okay. Something like this would work. Okay. Now let's try drawing a quintic function with a negative leading coefficient and 3 real zeros. And what that means is I can only cross the x-axis in 3 places. And I could have some turning points in there that are some critical points that aren't obvious. This one's not an obvious degree 5, so I like to make my turning points show that it's not going to make it to the x-axis, something like this. And you see there are 1, 2, 3, 4 obvious critical points, they're turning points, but only 3 real zeros. And the fact that it's negative means it starts up at positive infinity for y and ends down at negative infinity. Now I could do, there's an infinite amount of answers. Give myself some space between the first 2 real zeros, show a squiggle in there, and then something like this. Okay, but it must start up at positive infinity on the left and end on the right at negative infinity. Why don't you try drawing a quartic function that has a double zero at 3, zeros at 1 and 5, and has a y-intercept of 0, 6. You may not feel comfortable yet, but if you think about it, there's some definite points you'll put dots for, and from there, just kind of fill in the blanks. Okay, here's a possibility. If we make the 0, 6, and we plot the points 1, 3, and 5, we see that we must have a double zero, and I put the double zero at 3 there, so it bounces off the x-axis. Another option would be something like this. Now what's the difference between these two graphs? One opens down, one opens up. We would know that this one has a negative leading coefficient, and this one on the right has a positive leading coefficient. We're done with the lesson. This is the on your own question. Work on this and we'll talk in class.